Welcome back to Chapter 11 video notes for Chemistry 1510. We're going to pick up where we left off. We had just finished talking about intermolecular forces, and now let's look at how those intermolecular forces affect things like the properties of compounds. So when we start considering those intermolecular forces, they really do have a great effect on how a molecule behaves. And when I say a molecule behaves, I'm talking, is it a solid, liquid, gas at room temperature, and things like that. So we touched on this briefly at the end of the last video, that things that can maybe things that can hydrogen bond, or even things that are ionic. So ionic or potential hydrogen bonding here can be solid at room temperature. So if the intermolecular forces are really strong, then we're going to see that those molecules are really close together and they retain a very fixed shape. If we have something that maybe has hydrogen bonding, or maybe dipole-dipole, or even some instances you could have something that has London dispersion forces, but it's just a really big molecule. Those are going to be usually liquids. They have stronger attractions than things that maybe have just London dispersion forces, which would have very weak attractions and only really exist as gases unless the molecule is really big. And so these are just some general ideas. These aren't like set in stone. There are, of course, exceptions to these, but in general, the stronger the intermolecular force, you are going to see that be more likely be a solid or a liquid. Things with very weak intermolecular forces will tend to be gases. So for example, something like methane that has very weak intermolecular forces is the gas that you use to heat your house. Whereas something with stronger intermolecular forces like water, we see exist as a liquid at room temperature, and something with even stronger intermolecular forces of an ionic attraction is going to be a solid. Well, this is table salt at room temperature. So we see that there are some significant differences between the state that we see at room temperature, and then, of course, relating that to whether or not we have a strong intermolecular force or a weak one. Let's look at the next thing that we can relate intermolecular forces to, and that is surface tension. You've seen surface tension in scenarios in real life. Maybe you've done one of those cute things where you have a penny and you drop water onto the penny, and eventually on the penny there's like this dome of water, and that dome of water eventually breaks. Or maybe you've seen one of those videos where you have a little cup of water, and they lay a needle on top of it. I'm hesitant to use the little water bugs that seem to be able, oh, there's my water bug. He looks silly, to walk on water, because that's not technically surface tension. That's something different, even though it appears to be surface tension at first glance. Maybe if you go and YouTube search a video after this where you have a faucet of water, or a faucet, and you have water dripping out of the faucet, what you're going to see if you do it in like slow motion is this very interesting effect where you start to get like a little bubble at the tip of the faucet, and then it gains mass, it gains mass, it gains mass, and then it turns into this sphere once it has enough mass to drip away from the faucet. Maybe you've seen it where you have been in lab and you have a test tube, and your test tube has some water in it, and in order for you to pour that water out, it kind of got stuck in the top, and you really had to just go ahead and pour it out. Or maybe you remember when we were in lab, seeing the burette, the curve of the meniscus, right? That can be a form of surface tension as well. So we have all these real life examples of surface tension, but what the heck is it? And so I've got it here in words. And what happens in surface tension is you have the molecules that are on the outside of the sample, and then these are the inside molecules. And what you notice about the molecules in the inside is they have equal forces pulling on them every direction, whereas those outside molecules, they are attracted to, you know, these ones and nothing at the top. And so what happens is, because they don't have any molecules over here to be attracted to, they're really attracted to the ones that are next to them on the surface. And this kind of forms a film. And that film is difficult to break through. And it's not really difficult, you know, like difficult is relative. If you wanted to stick your finger through the surfaces of a cup of water, you could do that no problem. But those molecules on the outside are going to be more strongly held than, well, maybe I don't want to say more strongly held. It'll be more difficult to penetrate the water from the outside than it is to take an object that's already penetrated the surface and push it down deeper into the water. And so let's talk about how intermolecular forces and surface tension, oh goodness, are related to one another. So we'll scroll back up here in a moment. Oh my. And look at our surface tension. Oh, for heaven's sakes. Okay, so intermolecular forces and surface tension. If we have stronger, right, so we're comparing two things. If we have stronger intermolecular forces, which we abbreviate as IMF, then we're going to see a stronger surface tension. Because remember that surface tension is the attraction between, or the unequal attraction that you're experiencing from an outer molecule versus an inner molecule. So if surface tension at the heart is really about attractions, then what you will find is that the stronger the attractions, the stronger the surface tension. And so water, which experiences hydrogen bonding, is going to have a pretty high surface tension in comparison to things that don't have hydrogen bonding. So maybe, oh goodness, I don't know if you've ever experienced acetone before. But something like acetone, which is usually found in nail polish remover, right? That would be something that only has dipole forces, but it might be difficult for you to see or feel a difference between the surface tension of something like acetone and the surface tension of something like water. So let's keep talking about water. And let's talk about water in a different context. Here we're going to talk about something called wetting. And wetting is when you have a liquid spread across a solid surface. And so down here I have some pictures of wetting. And what I'm trying to describe here is this is glass and this is water. Over here, same idea, glass, water. The difference is here, that highlighted pink part, I have wax. So in order for wetting to happen, and the wetting is just the spreading out of water over glass in this case, what needs to happen is they have to have similar intermolecular forces. Oops, that's a P. I wanted F. So we need similar intermolecular forces in order for this spreading out to happen. And so if you have ever experienced something like this, where you see water, you know, on your windshield, maybe that water is from dew from the morning, or from a very light rain, right? It just spreads out over your windshield. But if you are someone who is really into cars, you often wax your car. And what the wax does is you now have a barrier between the glass, which is polar, and the water, which is polar. And now you have this non-polar barrier. And so when we look at similar intermolecular forces, things that have hydrogen bonding and dipole-dipole, those are polar. Whereas things that just have London forces, those are nonpolar. So your wax here is your barrier between the polar water and the polar glass. And so if you've ever seen it rain on a freshly waxed car, that wax causes the water molecules to just bead up into those little balls, and they just roll right off, right? So that doesn't allow things to be wet. All right, let's look at solubility as well. So, solubility. There's this cute little saying, like dissolves like. When I was a student, I didn't have a darn clue what they were talking about when they were saying like dissolves like, as though it was meant to mean something to me. What they really mean is polar dissolves polar, and nonpolar dissolves nonpolar. So like is talking about like polarity. So things that have like polarity will dissolve each other. And just in case you're unaware, the word miscible is when two liquids will dissolve in each other. And I think there's some stipulation where it's like in any proportion. So oil's a liquid, it's nonpolar. Water's a liquid, it's polar. Do they dissolve in each other? Or in other words, are they miscible? And the answer is a big no, because they do not have like polarities, right? They both have to be polar, or they both have to need nonpolar in order for them to dissolve. So think about it. Think about you putting, I don't know, oil on your hands, right? You just, oh gosh, of course the example that pops into my mind is you've massaged kale in oil, which is something you'll all laugh at because I'm sure you've never massaged kale with oil. So let's think of something different. Imagine you just put Vaseline on your hands, or butter, right? Your hands have butter on them, and you go to wash your hands, and just the water just absolutely beads off. It doesn't actually rinse off any of that butter or oil, because they're not miscible in each other. All right, now imagine a different scenario. You got water is polar. I'm sorry, ethanol is polar. Water is nonpolar. Oh, poop, it's too late at night. Ethanol is polar. Water is polar. Are they miscible? Yes. And for those of you who are 21 and over, if you've ever went to Meijer and purchased vodka, right? Ethanol is the thing that you would call alcohol, and water is also in vodka. And if you look at a vodka bottle, you are certainly not seeing layers, right? That is all one homogeneous solution, right? They are miscible in each other. Okay, now imagine that You have Vaseline, which is nonpolar. You have synthetic latex, has all carbon-carbon bonds and carbon-hydrogen bonds, also nonpolar. Are these two things soluble? Absolutely. Right? Nonpolar and nonpolar, they dissolve one another. This is kind of a crazy example because, you know, Vaseline is a solid essentially, right? And latex, think of like your rubber gloves. We don't actually use latex gloves in lab because some people have latex allergies. But if you took Vaseline and you got Vaseline on your latex glove while you were in lab, eventually your glove would start to dissolve. It's really wild. So then our final one is dirt is nonpolar, water is polar. Are they soluble in each other? And that is a no. Of course they are not, right? We have different solubilities there, or I'm sorry, different polarities there. So then my subsequent question is, why in the world do we use water to wash dirty clothing? And that's where detergents and soap come in. When you start talking about detergents and soap are special. They help the water rinse away the dirt. And so if we look at this picture off to the right over here, we have water, and then we have these little weird drawings. And the weird drawings are like a little squiggle and then a little something, a little circle. That circle is meant to be the end or the tail of a detergent. And a lot of detergents and soaps have this ending. And this ending is very much polar. How do I know it's polar? It's ionic. It's got a negative charge right there. In addition to this, you got a big old polar bond right there and a polar bond over here, plus this ion. So this part is polar. Now, this little squiggly line over here, this is actually, I just drew a squiggly line under squiggly line. Let's try that again. So this part right here is meant to be a carbon and hydrogen chain. So it's all carbons, carbon-carbon bonds with hydrogens coming off. So that is nonpolar. So what we have is one molecule that has a polar part and a nonpolar part. So in the center here, that is supposed to be your dirt. So that's your dirt molecule. And then you have your soap molecule where the tail is sticking into the dirt to help solubilize that. And then you have the head, which is your polar part. And look how it's forming like this circle around. Well, I guess it's a sphere, huh? It's forming this sphere. And we've just cut a little chunk out of the sphere so we could see the inside. So it's forming this negatively charged sphere. And so we have two ends to this molecule. So one end is kind of poking into the dirt molecule and solubilizing that. And the other end is forming what's a micelle, right? So a big sphere around the dirt molecule. So this polar end is called hydrophilic. So philic means love and hydro is water. So the hydrophilic end has a negative charge. It is ionic and very polar and thus dissolves in water. The hydrophobic end, phobic is like scared of, right? So the end that is scared of the water is going to dissolve in the dirt. And so that's how soap works, right? And so that's why we use water to wash away our dirt on our clothing, is it's really, you need that intermediate of soap. You need the soap to solubilize the dirt and then the water to whisk the little micelles away. So let's end with viscosity. When we talk about viscosity, the definition of viscosity is measuring the resistance of a liquid to flowing. And now it says here to visualize pouring nail polish remover in antifreeze. I don't know if I've ever had a student pour nail polish remover in antifreeze. So maybe what you want to imagine is pouring syrup, right? So if we pour syrup, everybody can recognize that pouring syrup is a lot different than pouring water. So what you're going to find is that something that has stronger intermolecular force is going to be more viscous. I wonder if I spelled that right. I don't know. I'll let you tell me. So it's going to be more viscous, and that means a greater resistance to flowing. So antifreeze happens to have the stronger intermolecular force. I have to tell you that at this moment because I haven't drawn that molecule for you. Nail polish remover, which is acetone, has a weaker intermolecular force of this pair. Antifreeze has hydrogen bonding, and it actually can do it in 2 areas in the molecule, whereas nail polish remover just has dipole forces. And so more viscous, we're expecting things that are more viscous to have a stronger intermolecular attraction. When we look at temperature, this is where the syrup example can really be a wonderful example. Some of you might prefer warm syrup on your pancakes, and so maybe what you do is you take some syrup and you warm it up. And so in order to do that, maybe you imagine taking the syrup that if you have real maple syrup you've stored in the refrigerator, and you take your real maple syrup in your big jug that you buy it at the farmer's market, and you take that and you pour it into a dish. And it takes a moment, right, for it to flow out. And then you take your dish full of syrup and you warm it up in the microwave. I'm pretending that I'm warming it on my stove. That's my fire that I just drew. And then you pour it onto your pancakes, and all of a sudden it just flows right over your pancakes. And then you think, goodness, now I have too much syrup on my pancakes. And so as the temperature is increased, what we see is that the viscosity actually decreases. Oh, goodness. Right, because remember, the viscosity is the resistance to flow. And so the resistance to flowing is decreasing as you warm up that sample. And so we're going to talk about these some more in class and hopefully bring in some demonstrations. So I think that's enough for tonight. Thanks for listening, and I'll see you soon. Katoni signing out.